Now it is section 9.3, back propagation. In the previous section, we saw an example of neural networks which uses the stochastic gradient descent method. In this section, we'll see how to compute the gradient, more precisely, the derivatives of the cost function with respect to weights and biases in all layers. This is the major part of the back propagation. The back propagation is a practical application of the chain rule for the computation of derivatives. Let's begin with notations. I'll explain the notations using pictures. Okay, here, layer by layer, between layers, we have the connections, and weights must be trained. So, for example, for layer 3, now here, these weights are existing because of this layer 3, so that we put superscript 3 for weight here, connecting layer 2 and layer 3. The out layer, target layer is layer 3. So we try to use now superscript 3. And this 2, 4 means that that is second on the here in the out layer, and fourth one in the in layer. So 1, 2, 3, 4. So in this way, we are making notation. And for the bias and activation, we are using the same convention. Here, layer 3, so that activation and superscript 3 and subscript means that the first one. Also for bias, here, the third one, so here subscript 3, and for layer 2, so that we put over there superscript 2. Okay, that's the notation. Then, with these notations, the activation AJL can be written in this way. From earlier layer, the previous layer activation, now weight up, and bias is added, and activation function is applied. That is making new, in the new layer, the next layer, activated value. Okay, and if we define this portion, the net input, weighted input, and here as ZJL, then, and also if we define here the weight matrix, a collection of these weights, and for Lth layer, and for Lth layer, now bias vector, and now here weighted input and activation, then this equation can be written in this way. In vector and metric equation, there's AL is sigma ZL, okay, using that, and this definition, it can be written in this way. And of course, ZL must be same as here, WL AL minus 1 plus BL. That is actually this one, right? Okay. Now, once we try to get the gradient, then we need to define cost function first. With the notations, the quadratic cost function can be formulated in this way. This is the label, the corresponding desired output, and that is activation value at the last, the layer, the output layer, and error is squared and summed, and here divided by n, the number of points, that is averaged value. Okay, here for the cost function, we need official assumptions, but already it is satisfying these assumptions, but anyway, we'll try to write down officially these assumptions. Now the cost function can be written as an average, already is an average form. Here the Cx is for individual training example. So here basically Cx will be that portion, half of that one is now Cx for each x, and here after adding, and here average 1 over n, right? And also here the second assumption is that the cost function can be written as a function of the outputs from the neural network. That is exactly here precisely AL, activation value at the last layer. So we are already using that term for the cost function. So most cost functions will satisfy this one. Okay? The reason we are making these official assumptions is here. And along with that assumptions, and here now Cx for individual x, the point, and that can be written in this way. And also, if we try to get gradient of the cost function, then that will be the average of the individual gradient, so that when we derive mathematics and we can focus on the cost function for individual point, so that we'll focus on each one over their Cx. Okay? So here, with the assumptions in mind, we may focus on computing the partial derivatives for a single example. Okay. For the backpropagation, there are 4 fundamental equations. Before deriving the equations, we define here the learning error. That is now in notation delta JL. L is for the layer. So for each layer, we define that. Now that is here partial derivative of C with respect to the weighted input. And that is alpha layer. For each layer, we define this one, and because it'll be used again, so that to make the notation simple, we try to use this definition. Okay, now we are ready to consider the 4 fundamental equations. Suppose that the cost function C satisfies the 2 assumptions in the earlier subsection. There's a number 1 and number 2, that one. So it is quite natural, and then most cost functions will satisfy these assumptions. And also, we assume the network contains L layers. It's not an assumption, in fact. And let's say there are L layers, okay? And then we consider the feed forward model given in this way. Okay, 9.10 is exactly that one. Here, then, here now, in last layer, the error, that is the learning error is now can be gotten this way. This is just a simple chain rule. And then now for the earlier the layers, the error can be written in this way. And once we get error, then now the gradient with respect to bias is exactly the error. And then the gradient, the derivative with respect to the weight must be here activation value times the error. So here, now it can be easily proved, and then we'll consider only this one in the proof, and the others are not so difficult. And this one is, in fact, the most difficult one here. Okay, so we'll try to prove B only, and you can do yourself for others. Okay, and exercise 1 is requiring for you to prove the others. Okay, here, and using the definition and the chain rule we have here. Now that is definition. DJL is now round C over round GLJ. Okay, here for that one, rather than okay, that one is first differentiated with now the next L plus 1, ZL plus 1, and then GL plus 1 now derivative with respect to ZJ. So it is a chain rule and must be summed over K. That is simple chain rule. And here in definition, that is now the delta L plus 1K, and then this is over there. And here now, ZK L plus 1 is from the feed forward network we defined in this way. And then that can be, okay, that one is also replaced by the sigma ZL, ZIL, and then in I summation over there. Okay, we use the definition here now. And this term, okay, here, that is the same as now here. This one will be differentiated with respect to ZJL. Then here, this rate, and then must be, this term must be differentiated with respect to ZJL. This is constant, so that this will disappear. And now this term is exactly same as sigma prime GZL. So we reach here, and including this one, combining, okay, this quantity the same as over there, we are putting over there, and we can get that one, right? So that we prove that. It's quite simple. It's a simple application of chain rule. For the others, you can prove them. Okay. Now, to formulate the 4 fundamental equations a better way, we need a little bit of a notation in a vector, matrix vector operation. One of them, very frequently used, the operation is element-wise product, and sometimes it's called Hadamard product or sure product. For example, C and D, vector or matrix, it doesn't matter. Just the CD product in J's component is now here from this one J's component, from this one J's component, and multiplication. So for example, 1, 2 is one vector, another one is, another vector is 34, then element-wise it is multiplied, and the final answer is 30 and 8. In NumPy, and A star B denotes the Hadamard product of A and B, and both should have the same size. It can be, they can be vectors or matrices. And if we want to get the matrix or vector matrix vector computation, then you have to use dot here command A dot B, or you have to use this notation in Python. Okay. Now, along with this Hadamard product notation, here the 4 fundamental equations shown in this equation can be written in this way. Now, delta L And first we try to get the error at the last layer, and backward way we try to get here the the delta L error, and from L minus 1 to 2. And the first layer start with the index start with 1, and we don't need get any the error for that because that is input layer, right? Okay, after getting these errors, and then now gradient with respect to B is just simply now the error, and then gradient with respect to W is now, and that is here the error times that activated value. And so that this product, it will be the gradient, okay? Along with math effector notation, here quite, it looks quite simple, okay? Okay, here we have a backpropagation algorithm. Now, this is designed for a single example, single point. Okay, input is X. Now, set the corresponding activation value A1, and then through feed forward, we decide here Z values, and then now here is activation value. And here output error can be computed in this way, and through backpropagation, we can get the earlier from back L minus 1 to 2, and earlier the error. And then once errors are obtained, then here we can get gradient with respect to B and with respect to W. That's for single the input point, so that here we have the final the algorithm for stochastic gradient descent method, and along with mini batch. So that here we choose M examples, M sample points, and here we initialize the change in W, change in B, and create change in W in 0, and then here for each example X, we try to get, by using backpropagation algorithm, try to get here gradients. And these gradients are added. So it's layer by layer. This is the last layer, and from second to last, and so that here B has a sort of the flat wide one, and here now there are from 2 to L the components, so that it's added, and for W also the same, it is added, and after adding for every point, the selected point, M points, and then here we try to averaging that divided by M, that is average value over M examples, and here we scale by using the learning rate eta, and negative of the gradient is now added to get the updated bias and weight. That is now the stochastic gradient, decent stochastic gradient learning method. Okay. Now here, and we see a remark here. Okay. That one. Okay. This one is that now you can see, once you are using, for example, the sigmoid function for activation, then here the shape of sigmoid function is, okay, here now And the value, okay, here is between now 0 and now 1, like that. So that is the highest one is 1, and that is 0. And once the activated value is around the 0 and 1, then around there, is very flat. So that the sigmoid function becomes very flat when the activation is approximately 0 and 1, so that its derivative will be almost 0. So along with this small value, now learning will be very slow. So that is called saturation. So here, and now here, if you are trying to get a fast convergent the network, then you have to choose the activation function very carefully. And suppose we were to choose a non-sigmoid activation function, so that its derivative is always positive, not around the 0, and never gets close to 0, then that will make your learning faster, so that it would prevent the slowdown of learning. If you are using sigmoid activation, then quite often it can happen, slow down. Here, learning accuracy and efficiency can be improved by finding more effective course and activation functions. So choices of the course functions and activation functions are quite important when you try to get very efficient and accurate the network. Okay. Okay, this is end of the section. Thank you.